Okay. So thank you again. Excited to walk you the journey through some highlights of the 4 big chapters that comprise my thesis titled Dynamic Decision Making Under Uncertainty in Electric Vehicle Routing and Logistics. So the fact that these vehicles are electric is a big part of the motivation of this work. And so I wanted to spend just a second to motivate why we are considering electric vehicles. So climate change is obviously happening at this point and is having negative consequences on the planet and eventually on all of us. And so it's important that all sectors begin to transition to practices that emit fewer emissions. And this is especially true in transportation, the green wedge here on the left, which was responsible for, this is specifically for United States emissions, this was responsible for about 1/3 of US emissions in 2017. And then within transportation, about 80% of emissions come specifically from vehicles. And so we in the vehicle routing community, it's important that we begin to consider electric vehicles which do not produce tailpipe emissions. And this has begun to happen at the consumer level, but also at large firms that use electric vehicles in their supply chain, such as Amazon, Budweiser, La Poste, UPS, and others around the world. So here's the flow of the projects that we will look at today. So we're going to start with a project on public charging stations. So EV routing with en route recharging at public charging stations. So en route recharging, this work was motivated by a study in 2018 by Villegas and et al. Specifically using Enedis as a case study. They have electric vehicles that their technicians use to visit customers. And while these technicians are visiting customers, they might need to recharge their electric vehicles. And so there's 2 options here. The first is to charge only at the depot. And the advantage of this is that you assume whenever you bring your electric vehicle to the depot to recharge, you can always begin recharging immediately. So there's no queuing time, but you might incur more travel time than the situation on the right here, where we've decided to use a public charging station. And so when we use the public charging station, we might incur less travel time to arrive. However, we incur potentially some unknown queuing time that we have to wait there. And so in the study by Villegas, they compared these 2 situations in the static case, and they found that the situation on the right, the en route recharging at public charging stations, allowed Enedis to save money, and it allowed them to use EVs for more routes. However, it introduced uncertainty, and so they ultimately chose to use the depot-only solution over on the left, which suggested that companies like Enedis need routing tools that are able to adapt to this uncertainty. And so that was the motivation for this project. And so we modeled this problem as a dynamic routing problem, which we modeled as a Markov decision process. And in a Markov decision process, we develop policies which choose actions from a given state. And here our policies are specifically designed to help respond to that uncertainty that we might encounter in terms of queue length at public charging stations. And our objective with these policies is to minimize the total time to serve all of the customers for this technician and then return to the depot. And then these policies, we solve them sort of in real time, right, using a simulator basically. And so we need some way to benchmark the performance of these policies. We want to know how good we are really doing. And so we call this bound a dual bound. And specifically here for this problem, we use the value of an optimal policy with perfect information. So basically what we do is we give this in an imaginary scenario, we give the technician access to all of the waiting times at every point in time, at every charging station in the instance. And we say, okay, if you know everything in advance, how much better could you do? And this is a difficult problem to solve. We did so using Bender's decomposition, where in the master problem, we search over customer sequences. So here we have the sequence 34512. And then in the subproblem, we insert charging decisions into that sequence so that that route becomes energy feasible. In the computational experiments for this study, so we used some real Enidus instances that were from that original study by Villegas and co-authors. So we used 34 instances that have an average of 16 customers and 49 charging stations. And we considered various levels of demand at those public charging stations. And in short, what we found was that by allowing our routing policies to take advantage of public charging stations, they outperform the depot-only en route recharging by about 25% on average. And we also found that our policies were competitive with that dual bound established using perfect information, about 13% in this case. And so that's all for this project. So now we're going to transition to a different environment for a ride-hailing project. So now we're going to consider a problem, dynamic ride-hailing with electric vehicles. And so what you can think of is something like an Uber or a Lyft fleet, where you have a handful of vehicles scattered across the field, and you have requests popping up like this one here that takes a customer from their home to their work. And these vehicles are able to idle or wait for future requests at charging stations that are located throughout some area that we're considering. And the two actions that we need to take in this particular problem are to assign vehicles to requests. And so here we have this central intelligence hub. So the drivers in this point have no control. Originally, this problem was assuming autonomous vehicles. So basically, everything can be controlled remotely from a control center. So one of the two types of actions that happens here is this assignment of vehicles here, the blue one, to serve a new request. And then we also want to proactively recharge and reposition these electric vehicles in anticipation of future requests. For instance, this vehicle down here in sort of the bottom middle being told to reposition and recharge to this charging station. So in this particular problem, we are again going to use the Bender's decomposition, these classical OR tools, to establish that dual bound. And here in the dynamic problem now, where we're developing a policy, we're now going to use deep reinforcement learning. So in the context of deep reinforcement learning, so we're still going to model this as a Markov decision process, but it just looks a little bit different when we talk about it in the context of deep reinforcement learning. So we now envision an agent that's interacting with an environment. And this agent observes a state from the environment. So here, a state that captures the whole problem would tell you the current time, where are the vehicles, what are they doing, and what are their charge levels. And it would also include information about the new request that just arose. And from a state, the agent chooses an action, which here consists of which vehicle do we want to assign to the new request. And for every vehicle in the fleet, do we want to give them new instructions for repositioning or recharging? Upon choosing an action, the agent then receives a reward from the environment. Here, it's equal to the value of a request if we have served one. And then we also receive a new state from the environment. And we continue this process until we hit some time limit. And our objective as the researcher is to develop an agent that maximizes the expected sum of rewards. So essentially, how can we serve as many requests as possible? So the two agents that I want to talk about that we developed, the first is our simple heuristic that we use as a comparison. So we call this one nearest, which basically assigns the nearest vehicle to serve a request. It doesn't do any proactive repositioning. But after a vehicle finishes serving a request, then it will assign that vehicle to go recharge at the nearest charging station available. And the second agent that I'd like to discuss is Drafter, which is what we called our agent that uses deep reinforcement learning, specifically deep Q learning in this case. And what it does is it uses a neural network to choose an action for every vehicle. And so every vehicle is basically thinking individually and asking, should I do nothing? Should I serve the new request? or should I go to one of the available charging stations, actions 2 through N there. We again want to see how we are doing. So how good are these policies? So we're again going to establish a dual bound by allowing the decision maker to have access to perfect information. And we're again going to solve this problem as using a Bender's decomposition. It's actually quite similar. So in the master problem, what we're going to do is going to assign customers to vehicles. And we do this in a way that is time feasible. So, for example, here, request 1 is assigned to vehicle 3, and requests 2 and 4 are assigned to vehicle 1, and 3 and 5 are assigned to vehicle 2. And then in the subproblem, we ensure that these assignments are energy feasible, and that and we also insert charging decisions into these schedules for each vehicle. So we basically we take a solution that doesn't know anything about energy requirements, and we make sure that it's energy feasible. In our computational results, we considered instances that resemble a business day in Manhattan in 2018, where we have 14 vehicles, which obviously is not like Manhattan, but a smaller instance set here. So 14 vehicles, and about 1,400 requests per day that show up for these vehicles to serve, and about 300 charging stations scattered across the island of Manhattan. And what we find is that our drafter agent trained with deep reinforcement learning outperformed our heuristic by about 16%. And then when we compare that to the dual bound, it's quite weak compared to the solution in the first problem, about a 34% gap between our best agent and our dual bound. But I would mention that in many dynamic problems, a good bound is not available. So just having this bound here was very useful to know the value of that information. OK, next, a couple smaller projects. So this first one is a Python library that we developed specifically to solve an FRVCP. So the FRVCP is the fixed route vehicle charging problem. So basically what this says is we have a sequence of customers that we want to visit, and we want to know how to make that route energy feasible for an electric vehicle. And this is quite a complex problem. There are many possible detours to charging stations that you could make, and many different battery levels that you could charge to at each one of these stops. So this is an NP-hard problem. And an efficient algorithm was developed to solve this problem by Froger and co-authors in 2019. But this algorithm is notoriously difficult to implement. And so we basically developed that algorithm inside this open source Python library for the community to use. And it's applicable across a wide range of electric vehicle routing problems. So very excited for this to be available for the community. Now for this last chapter, a bit unusual and not very much like the previous chapters. We're looking at taking a vehicle routing problem and turning it into a video game. So some of these artificial intelligence projects have been very popular in the news, where we've seen Google playing chess and Go and poker and the game of StarCraft. But one of the first studies was for Atari. And in the case of Atari, they basically developed one artificial intelligence, one AI, or at least one type of AI. And they exposed it to many different Atari games. And across many of these games, it outperformed humans. It reached a very impressive level. And so this was a very notable achievement because these games are quite diverse. Sometimes you're shooting something and moving up and down, and sometimes you are moving left and right, and sometimes you are jumping around. You're a little character jumping around in the game. So they're very different. And so the fact that one type of AI was able to solve all of these different games made us wonder if we could turn our VRP into an Atari game, would it then be playable or solvable by this artificial intelligence? And I realize I'm running over on time here, so I'll go quickly. But basically what we wanted to do was take a simple VRP. Here we chose the VRP with stochastic service requests. And we wanted to turn it into a video game and see if we could use the existing artificial intelligence developed by basically these Google researchers to beat our VRP. And so the game that we developed for the VRP SSR has a single vehicle here, the pink square that starts at a central depot, the blue square, and it has to visit some customers. Excuse me, it doesn't have to visit, but it wants to visit as many customers as possible before the time has expired. And so the green customers we know have already submitted a request for service. The orange customers might submit a request for service, or they might not. And we don't know when they will request service. And so the vehicle wants to serve as many of these customers as possible before the end of some time horizon, which is captured in the video game by this bar at the top, which shrinks as time goes on. And the actions for the vehicle here, so conventionally, you would choose a customer to visit, and you would move directly to that customer, and then you would choose another customer to visit. In the case of the video game, you would move up, down, left, right as your action. So one square, move. And a short summary of the results here. So we were able to build an agent that was similar to the original Atari agent. We had some success tackling a visual representation of our VRP, but it certainly did not yet compete with traditional methods. So don't get rid of your operations research tools yet. But it was a fun project to work on, and we're actually still working on this project, and so maybe we'll have some news eventually. But for now, this is my last slide. I just wanted to share with you an image of our agent running around and serving customers on the board. But that is the end of my presentation, so I'm happy to take questions.
Merci Nicolas pour cette présentation. Donc je vais donner la parole à Marie-Ange d'abord et puis à Ammar ensuite.
Merci Marc. Je pose mes questions en anglais ou en français, je ne sais pas.
Si possible, anglais meilleur pour moi, mais
okay.
Totalement OK.
Avec mon mauvais anglais, je vais essayer. OK.
Avec mon
So, thank you for this presentation, Nicolas, and congratulations for this very complete and innovative work. And I was sometimes rather surprised and pleasantly surprised by your original way to approach some of the problem you deal with. And so in your thesis, you have solved the three transportation problems, which can have several and different applications, and you have validated your methods on instances which were drawn from practical cases. Then I have some questions about the possibility, the possible applications of your work. Mm-hmm. My first question is about the first problem. And in your work, you consider the global time as your objective function. So it's the sum of the traveling time, the waiting time at charging station, and so on. Mm-hmm. And you obtain, you said you obtain 25% improvement compared with a private-only charging mode. Nevertheless, I suppose that charging a vehicle at a public station could be more expensive than charging it at a private station. Mm-hmm. And it seems to me that you don't consider such an operating cost in your work. So I wonder which would be the impact on the models and the bounds and the results if you consider such costs. So have you ever thought about this question, that to change the parameters used in the objective function? And if so, can you provide us with some answers, maybe?
I wish, so this is a great question. I wish I had sort of numerical results to give you for this alternative objective. I don't. It was something we considered at the beginning. whether or not we wanted to use time or cost for our objective. The reason we chose this particular objective, so for EDF, for Enedis, it is possible that they might want to use, they might establish a charging station in the field for their own use. But for this particular problem, we were considering smaller logistics providers that might not have the financial resources to build a charging station in the field. And so if the time for them to complete their route was fastest, we assumed that that was more important than the cost they might spend at the charging station, which is usually the cost to recharge a vehicle is not that large, especially for a vehicle that does need en route recharging. These typically have a smaller battery, and so the total energy consumed to charge it only requires less than the cost of a tank of gas, for example. So our assumption was that time was more important. In terms of the modeling impacts, so I believe the same modeling approach would work. I think still a Markov decision process. But now as you travel along arcs, the costs incurred, I suppose as you move along an arc between customers, you would incur some potentially some negative costs. Actually, in terms of the energy you've depleted. Yeah, I think you could work these costs onto the arcs in the tree for the Markov decision process. The bounds would also be, so if we just included costs, I think it would make this problem even more difficult, because you still have to consider the time to basically, you would want to incorporate time in there somehow, basically by paying your technician as they're performing the service, right? So you still effectively want to minimize cost while you're doing this, but you would also be including an additional cost. So I don't think it would make the problem any easier to solve, unfortunately. But yeah, no, this is something that that we didn't study quantitatively. It was it happened in the very early stages of this work when I was still an intern at Tours, before I was a formal student. This is a great question, though. Thank you.
Okay, there's no problem. The time is often the main parameter which is considered, but it will be interesting to add other operating parameters, I think.
I agree.
So to be sure that your method can be okay for many applications. Okay.
Yes.
Maybe a second question, if I can. Marc, le temps? In the problem, which problem? The VRP with stochastic service requests.
Mm-hmm.
The modeling which uses Atari field formulation, which is very original, enables in particular to consider preemption of demands. Okay, which could be very interesting. Mm-hmm. And you say that it consists in altering the vehicle's path to join a different destination. Mm-hmm. But in the same way, it may suppose that the current customer accepts a longer route, which is not always realistic. It depends of the application and okay. So in which cases can we find such a situation where the preemption is interesting and is accepted?
Yes, so we did have, so in order to formulate any VRP in this sort of video game style, we had to cut many corners. There were many realistic constraints that, at least for now, cannot be captured in a visual way. And so I don't think that Atari would be good. So for example, I don't think that this approach would work well for a multi-vehicle routing problem. I think it would be very difficult to have control over multiple vehicles with a single joystick, a single controller, if you will. In terms of the the instances where preemption would be okay, I feel like pickup problems are one. So pickup of goods rather than people. I don't think anyone would be disappointed about their package taking a longer route back to the depot. However, another constraint, and I'm exposing the negative sides of this work, but another constraint that would be very difficult to capture in an Atari game would be a service requirement, being able to assure a customer that their package would be picked up. So there are other ways that we could potentially model this problem. Basically, rather than getting a point for every square visited, we could instead force the vehicle to visit every customer, but just subtract a point for every minute that they are away from the depot. So there are ways, I think, that you could guarantee service requirements, but it would not work in the same way, and it would not be as good as in the classical operations research context. Okay,
I think that it would be interesting to work more in this way, because, for example, even in person applications, you take taxi instances, for example, and maybe you can imagine that some customers agree to accept a longer route, maybe if it decreases the cost. Why not? So
yes, yeah. Why not? And absolutely, the current solution, I think, could handle this preemption and keep customers on board, assuming your vehicle had capacity. I worry that it might not be implementable just because, at least directly from the Atari game, because somebody could be theoretically on board the vehicle for the entire, they could be the first one picked up and the absolute last person dropped off. We don't have any constraints right now that would prevent that from happening.
Okay, just sorry for interrupting, but we should give a few minutes to Ammar to ask questions.
Thank you.
Thank you, Marc. Thank you, Nicolas, for this nice presentation. I really appreciate your work on combining this machine learning approach with the optimization problem. I have just a question about, I extended the question of Marie-Ange about this, the charging cost. If you consider, we can see that even minimizing the total time is interesting in this case, but also we cannot avoid considering the cost of charging. Perhaps what we can consider there is for instance, an hierarchical objective. Given how can you minimize the total time given the budget of charging? In this case, perhaps how can your approach can be extended or can validated when we consider a budget for charging?
Yes, a great question. So I think for the dual bound, for the sort of the static perfect information version of that problem, I think that could be basically incorporated into the objective as basically a penalty in the objective function with some constraint that we don't want to spend more than a certain amount on charging costs, for example. In terms of the dynamic problem, implementing a hierarchical objective, I am actually not familiar with how you could do that in a Markov decision process. My first instinct is that you could potentially, you would have to convert them to one unit, basically, and then you could still incur some weighted combination of costs along the arcs in your decision tree. I think you would also have to you'd have to add new constraints to your action space as well. I think you would when you're charging, if we set some bounds on, basically the duration of charging or the amount of money that we're willing to spend during a charging stop, that would impact your action space, basically shrink the size of the actions that would be available to the decision maker. And actually, this would be very difficult to implement specifically in the labeling algorithm that's used in the subproblem for the dual bound. I think this would be a non-trivial addition to the problem.
Okay, thank you very much. I think I can stop here, Mark.
Thank you.